Okay, so I just checked, and all of these little segments for Dijkstra's algorithm and Bellman-Ford sum up to almost 70 minutes. So I'm not going to get to Floyd-Warshall in this lecture, but I'll try to get most of the way through the idea of how to use matrix multiplication, or something like matrix multiplication. So far we've been talking about single source shortest path algorithms. So these, you choose a source vertex and then find the distance to everything else. So now we're going to talk about all pairs shortest path. So if you used Dijkstra's to do this, then it would be the complexity of Dijkstra's times n. Excuse me. Complexity of Dijkstra's times n, so that would be, we saw it was n log n plus m, so it would be n squared log n, or n times m. So m can be as bad as n squared, so this could be cubic. That's actually not too bad. It's actually as good as what we're going to get with Floyd-Warshall, but Dijkstra's doesn't handle negative edge weights. So if we wanted to use Bellman-Ford, then we would remember Bellman-Ford is v times e, or n times m. So now it would be n squared times m, and if m is something like n squared, you get n to the fourth, which is pretty horrible. So the first thing we're going to see is an algorithm for doing this, computing all of the distance between all of the pairs using something that looks like matrix multiplication. This was why people are excited about Strauss's algorithm, because if you can speed up things like matrix multiplication, you can speed up a lot of other algorithms. Okay, so bearing in mind that I only have, I think, 11 minutes to give this idea, I'm just going to zip through it, and then I'll do maybe the first half of Wednesday will be Floyd-Warshall, which is not too different from this. So here's a graph. This is the example from the textbook. It has a negative edge weight. It doesn't have a negative weight cycle. However, so suppose that, so this is, if you just look at this thing over here, this matrix, this tells you the distance between any pair of vertices where you can go between them in one step. Okay, so for example, to go from 1 to 2 in at most one step. From 1 to 2, you look at the first row on the second column, and it's a 3. Okay, the thing is, it's at most one step because you're allowed to sit still. So you can't go from 1 to 1 in exactly one step, but it still costs 0 because you can waive the right to take a step and just sit there at cost 0. So the idea is, how would you, if you have the matrix for the distance matrix for the cost of moving between vertices using at most one step. So if you can't go, for example, between 1 and 4, the cost is infinite. So the cost of going from 1 to 4 in at most one step is infinite. So now, how do you compute the cost of going from some vertex I to some other vertex j in at most 2 steps? Well, let's suppose that we've picked I and j. So we would say, oops, what we could do is just do a little for loop and say, okay, our estimate of the cost in at most two steps of going from I to j is infinite. And then for every vertex k, for k and v, we look at the cost of going from I to k in at most one step, and the cost of going from k to j in at most one step. And if that's less than our current estimate of the cost of going from I to j in at most 2 steps, then we update our estimate. Okay, so it's basically just a min over the choice of k, And so this isn't very complicated because now we'd have to nest this in a for loop for I and a for loop for j. So it'd be 3 nested for loops, which actually should look, now that you know we're going to be doing something like matrix multiplication, you should think, okay, that is when you multiply two matrices to work out for the product for the entry in the ith row on jth column of the product, what do? Well, to work out the whole matrix, you loop over I and j, and to work out the entry in the ith row in the jth column, you take the sum over the products of, you work along the ith row in one matrix and the jth column in the other matrix, and you multiply each of the corresponding entries as you work along the row and down the column, and then you take the sum. Okay? So to work out the matrix multiplication, you would do something like this for j and v, for I and v, for j and v, and then you'd say, okay, the sum is equal to 0, and then for k would go, so k would go along the length of the row and down the height of the column, and you would just add the product of the two entries. But here you're not taking the sum of the products, you're taking the min of the sums. Okay, so it's a little bit different, but the structure is the same. So to see how that works, let's look here. So we've written the distance matrix twice. So let's suppose that we want to work out the distance in at most 2 steps from 2 to 3. So the idea is, well, we have the distances from 2 to everything else, and we have the distances from everything else to 3. So we're going to take the min over infinity plus 8, and 0 plus infinity, and infinity plus 0, and 1 plus minus 5, and 7 plus infinity. Okay? So that's going to be, here it would be 2 going to 1. Well, you can't actually get from 2 to 1 in 1. 2 going to 2, 2 going to 3 is infinite. 2 going to 4 is 1, cost 1. And 2 going to 5 is cost 7. And then here, this is cost of 1 going to 3, which is 8. And 2 going to 3, which is infinite. And 3 going to 3, which is 0. And 4 going to 3, which is minus 5. And 5 going to 3, which is infinite. So here, it's the minimum of these sums is 1 plus minus 5, and that's going from 2 to 4, and then going from 4 to 3. Okay? So we would do that. So this is, if instead of min, I put sum, and instead of all of these sums, I put products, it would be working out the ith row and the jth, the entry in the ith row and jth column of the product of these two matrices. Okay, so it's a distance matrix, so it's square, so you actually can do the multiplication. You don't have to worry about transposes in this case. Okay, so how long does this take? Well, it takes cubic time, and you can actually, there is an algorithm called Seidel's algorithm, which actually uses tricks to get fast matrix multiplication to speed this up. But I'm not going to go into that in my remaining 2 minutes. So if you do this, well, well, this gives you the distance at most 2, and then you think, okay, so that's going to take cubic time, for the same reason that you naively do matrix multiplication, it takes cubic time. So if you want to work out, now, assuming that there's no negative weight cycle, and you can detect a negative weight cycle the same way you can detect it with Bellman-Ford, because at the end, if if you've got the estimates, and then you go through and check the edges. If there's a negative weight cycle, then one of the edges can't be right, for the same reason in Bellman-Ford. So if you did this and said, okay, everything's going to be assuming there's no negative weight cycle, all of the shortest paths between any two things are going to be length of most n. So I just have to take the nth power, do this n times, and that's going to give us n to the 4, which is as bad as running Bellman-Ford from every vertex. So that's annoying. But then there's a trick which you should know, even though I have 20 seconds left, but bear with me, called repeated squaring. So what you do is you don't take this matrix and multiply it by itself, and then multiply the result by the same matrix, and multiply the result by the same matrix. Instead, what you do is you take this and multiply it by itself, and that gives you that squared. And then take that and multiply it by, take the product and multiply by itself. So this squared multiplied by itself gives you this to the 4th. And then take that product and square it, and it gives you this to the 8th. So in each step, you're getting the minimum cost of going from any vertex I to any vertex j in at most 1 step, at most 2 steps, and at most 4 steps, and at most 8 steps, and at most 16 steps, etc., etc. How many times do you have to do this? Log n. So you actually get n cubed log n. So that's kind of neat. Repeated squaring is really useful. Please remember it. And so you got something that's easy to program and easy to remember, and is fairly fast. And you can, I mean, if the matrix is sparse, you can use tricks to speed it up. Okay. And so that's n cubed log n, and then on Wednesday we're going to see Floyd-Warshall, which gets rid of the log n, so it gets you down to n cubed. And it's similar, but you just have to so it's dynamic programming to avoid some of the work. I think I'm a bit over time. I'm done. It's been a tough day. Good luck. So see you Wednesday. Good luck with assignment 4 is what's due now, I think. Okay, cheers.